Okay, we're going to start with a check your understanding that you guys were supposed to complete yesterday. Number 1, it says half of the graph of an odd function is shown below. Sketch the other half of the function. So the only half that we were given was listed here. And remember what we learned yesterday. If I have opposite signed x's on an odd function, that gives opposite signed y's. So if I think about here, this is the ordered pair up here is the ordered pair 0, 3. So opposite signed would be a negative 0, which again is just 0, and then negative 3 for the y. So I have 0, negative 3 here. If I think about the next critical point that I can really spot, it's here at 3, 0. So if you think about the opposite signed x, negative 3 gives an opposite signed y. So negative 0 is still 0. And if you think about this point here, this point is at the ordered pair 7, negative 2, which means an opposite signed x, negative 7, would give an opposite signed y, positive 2. And so really from those 3 critical points, you can get a good enough graph of the rest of it to make it look symmetric. Number 2, if 3, negative 18 is a point on a graph of an even function, what's another point that you know must be on the graph? So again, just to review, for an even function, opposite signed x give the same y values for even functions. So if I know 3, negative 18 is on the graph, opposite signed x gives the same signed y. So negative 3, negative 18. 3, if y equals x to the 5th plus x to the 3rd plus 3 is y equals x to the 5th plus x to the 3rd plus 3 an even function, an odd function, or neither, and then prove your work algebraically. So either way, if I have to prove my work algebraically, I'm plugging in a negative x everywhere there used to be an x. So this becomes negative x to the 5th. This becomes negative x to the 3rd. Nowhere to plug in here. Negative x to the 5th is a negative x to the 5th because it's an odd power. Negative x to the 3rd becomes a negative x to the 3rd, and then plus 3. So to be even, it must look exactly like the original. It doesn't. To be odd, every sign must be different. Well, 2 of the signs are different, but the last sign is still a positive 3. So it's not odd either. So it's neither even or odd, which means it doesn't have either one of those symmetries. Not symmetric with the y-axis, not symmetric with the origin. A quick way that you can tell this without proving it algebraically, again here you would have to prove it algebraically because it asked for you to. But if you didn't want to prove it algebraically, just really quickly, look at all your powers. This is an odd power, and then if I have a constant term, that's the same thing as having an x to the 0 power. So that's an even power. So for my 3 terms, I have an odd power, and an even power. That's neither because they're mismatched. If all the powers are odd, it turns out it's an odd function. If all the powers are even, it turns out it's an even function. 4, true or false? If the statement is true, explain why it must be true using the definitions of even and odd. If it's false, just give one counterexample. So it says all even functions must go through the origin. So an even function can go through the origin, but they don't have to. Think about drawing any parabola whose vertex is not the origin, but it's somewhere on the y-axis. That will give you a parabola that has symmetry through the y-axis. That makes it be even. I don't know why they put this equation with this graph. Those are not the same. This is a negative x squared minus 2. This one's positive, but here, this is just another counterexample. B, if each term in a polynomial function has an even exponent, the function must be even. Well, I kind of just ruined this, and I didn't even know it. You guys know I don't read ahead like I'm supposed to. So if every term in a polynomial has an even exponent, then when I plug in and square it, or raise it to the 4th, or raise it to the 6th, it becomes the positive of that negative x that I plugged in. So because everything becomes positive, that means everything will match the sign that it was originally. And so it actually turns out it is even. So again, just the shortcut. If every power is even, then the function is even. If every power is odd, the function is odd. If there's mismatched even and odd powers, then it's neither. So as we're beginning this next page, I just want to remind you that you are going to have those Canvas assignments due this week, 2.1, 2.2, and 1.5. We're looking at the end is in sight. So we're kind of looking at end behavior of graphs. So it says, what happens when we evaluate polynomials at very large positive numbers and very large negative numbers? How does that manifest on the graph? Let's investigate. So what they're saying is, if I plug in x's that are really, really big numbers or really, really small numbers, and when I mean small, I mean like negative 1,000 or negative 100, then they want to know what's happening at the graph at that point. So if I plugged in a 100 as an x value, and I raised 100 to the 5th power, that's going to be a very large number. It's going to be positive and it's going to be large. So when I plug in 100, the y value I get is something that's very, very big. It's positive. So all they want to know is it positive or negative? This one is positive. Here, if we plugged in 800 and squared it. So if you think about it, this value is going to be a very big positive number. Times by negative 2 is going to give a negative value. So if I plug in a very large number like 800, in this function it gives a negative y value. For e, if you think about a negative number raised to an odd power. So negative times a negative times a negative times a negative times a negative. I don't know what that number is, but I know it's going to be negative something. So this part of the term is a negative number, and it's going to be multiplied by negative 6. So a negative times a negative gives a positive. B, if I raise a negative number to an even power, it gives a positive output. And then D, if I raise a negative number to an odd power, that gives a negative output. Okay, 2. Consider f of x equals x cubed plus 5. What happens to the y values as the x values get bigger and bigger? And then you can just try a few values to investigate. So I'm just going to think, what if I plugged in 100 here for x? Well, 100 cubed, that's going to be a positive number. And then plus 5 is just going to make it a little more positive. So as I plug in really big x's, the y values get bigger and bigger. And that would keep happening if you plugged in 1,000. Think about it. 1,000 to the 3rd is a big number. Add 5, it's still positive. So as the x values get bigger and bigger, the y values also get bigger. So what I would say here is as x gets bigger, y gets bigger. And then B, what happens to the y values as the x's decrease without bound? So let's think about if I plugged in negative 100. So negative raised to a 3rd power, that's going to give me a negative value. Adding 5 is not going to change it that much. It's going to raise it a little bit, but it's still going to be very negative. And then just think, if I plugged in negative 1,000, it would get even more negative, because negative to the 3rd power is negative. Plus 5, again, doesn't do much to it. So as the x values decrease, the y values also decrease. So we have ways to talk about this using what's called limit notation. So as you do more in calculus, if you take a calculus class, you will use more and more in limit notation. But let's just kind of draw it out and talk about what this means. So for number 2, if I wanted to answer this in the fancy limit notation, we could say the limit as x approaches infinity. So all this is saying is, as my x's get larger and larger and larger and get closer to positive infinity, as the x's get bigger, what happened to the y values? They also got bigger. So the limit as x approaches infinity of our function f of x is equal to infinity. So all this is saying, as the x values get really big and close to infinity, the y values, remember f of x is another way to say y, the y values also go to infinity. Now, think about what you think number 3 would look like, 2b would look like in limit notation. So I would talk about the limit as x approaches. So if the x's are getting smaller and smaller and smaller, the x's are approaching negative infinity. So as we get closer and closer to negative infinity, what are the y values doing? They're also decreasing. So f of x is getting closer to negative infinity. 3 says, consider what happens to the y values as the x values get bigger and bigger, and then try a few values to investigate. So let's just think, if I plugged in 100 into this function. So that would be, let me get my calculator really quickly so I can get the value. But what we're leading into is an investigation on the leading term, or the highest powered term, and we'll see that as we get there. So in your calculators, plug in 100 to the function. So that would be 3 times 100 raised to the 4th minus 100 raised to the 3rd plus 5. So when I plugged in 100, I got a very large y value. And now if I go click on that value again and highlight it, I'm going to change it from 100 to 1,000 just to see what happens as the x's are increasing. So now I'd have 3 times 1,000 raised to the 4th. So I'll take a picture of what I've done in my calculator to make sure you guys see the same thing. So you can see as I plugged in 100, my y value was 299 million. And now then, as I plugged in 1,000, that y value is getting bigger and bigger and bigger as well. So here, the limit, as the x's get really large towards infinity, the y's are also getting very large towards infinity. So what I want you guys to think about is, in this problem, if I plug in large numbers, this value is getting bigger and bigger and bigger because it's being raised to the 4th power, so this term gets bigger. This term would get smaller because raising 100 to the 3rd power is a large number, but there's a built-in negative out front. So this number is really big, and then I'm subtracting something that's very negative, and then adding 5. So which term is winning? Is the x of the 4th term? Think about them playing tug of war. This one's wanting to get really big. This one's wanting to go to negative infinity. Which term wins out? The one with a higher exponent wins out because the y's are still getting bigger. So whenever you have multiple terms like this, you can always look at the term with the highest exponent for its variable, the highest powered term. And that one is the one that wins the tug of war. So knowing that, if I look at B, what happens to the y values when the x's get really, really small? So knowing what we know now, the leading term is the one that matters. If we think about it, if my x's become very negative, well, a negative number raised to the 4th power is positive. And then times 3 is still positive. So the leading term is still positive. So I expect to get very high y values. So what you can do is plug in negative 100 into that same equation. So I'm going to put that in my calculator. I already have an idea of what I think is going to happen. Just remember, when you put in a negative 100, make sure you put that in parentheses. Because if not, it's going to ignore that negative you have out front. And then it'll be like a minus a negative. So right here is what I typed in for B, plugging in negative 100. 3 times negative 100 to the fourth minus negative 100 to the third plus 5. Notice it's getting very big again. So this leading term is still winning that tug of war. So what we would say here, the limit as the x's go towards negative infinity. As my x's get very, very small, the y values are still increasing. So f of x goes to positive infinity. Okay, look at part C here. See, how would your answers change in parts A and B if the function was negative 3x to the fourth minus x to the third plus 5? So again, think about this leading coefficient. If I plugged in a very positive x, positive raised to the fourth is positive, but then times negative 3 would be negative. So as the x's got really big, this term would become negative. Because, again, think about what's happened. There's been a reflection over the x-axis, right? So we're changing the signs of the y. So the limit as x approached positive infinity, the y's went to negative infinity. And then think about that same thing if I plug in a very negative number. So if I plug in negative 100, negative 100 to the fourth is a positive number. And then that positive number times negative 3 is going to be a negative number. So as I plug in negative values, the y's also become negative. Which again makes sense because what degree polynomial is this? It's a degree 4 polynomial. And if you think about the end behavior of a degree 4 polynomial, they have to both be in the same direction. So for A and B, they were both going to positive infinity for a 4th degree polynomial. And now for part C, they're both going to negative infinity. Again, even powered polynomial has agreeing end behavior. So it fits with what I think the answer should be. Okay, if I look at 4. 4 says the graph of the functions g of x equals negative 2x to the fifth and h of x equals negative 2x to the fifth plus 5x to the fourth minus 10 are both shown. So identify which graph is g and which graph is h. So the quick, easy way to identify which graph is which, I think, is by symmetry. So the one that's not dotted, the solid line, it has symmetry with the origin. So because it has symmetry with the origin, it must be an odd function. G is an odd function because its only power is an odd number. But H has an odd power and an even power. Therefore, it would have neither symmetry. So the solid line should be G and the dashed line should be H. And again, there's other ways you could identify it, but I think that's the easiest to me. Now, as I look at B, compare the end behavior of both graphs. So end behavior. So let's look. So for G, so I would say the limit as x approaches infinity of g of x. So what I'm saying is, looking at the solid line, as the x's go towards infinity, so as I go towards the right, x gets bigger and bigger and bigger. What's happening to the y values? The y values are decreasing, going down. So as x increases, y decreases. So as x goes to positive infinity, y goes to negative infinity. And now think about the same thing for h of x. it's in the same position. So the limit as x goes to infinity there for h of x is also negative infinity, because they're both heading downward as the graph goes to the right. Now I'm running out of space here, but hopefully you guys can fill out the rest of this. As the limit as x goes to negative infinity, so as the x's get smaller and smaller and smaller, what's happening to the y values? So as x goes towards negative infinity, the y values are increasing, which means we're going to positive infinity. So we could say the limit as x goes to negative infinity of g of x is positive infinity. And then 5, which term in the polynomial seems to have the biggest impact on the end behavior, and why do you think this? So we kind of, again, I've already ruined this, go figure. Polynomial functions are dominated by their leading term. And what that means is the term with the highest power. So the first term has the highest exponent, and so when x's get really, really large, it overpowers the rest of them. So that's kind of what they're wanting there on 5. So here are the quick notes that you can copy down. So today I want you to work on the check your understanding. I might go ahead and put the answers at the end of this slide, of this PowerPoint. That way I can keep everything in one video, kind of keep it all organized that way. But pause the video, don't just look at the answers. See if you can work them out. And then if you have any questions about the answers, let me know and I can work them out in the video tomorrow. Just send me an email and tell me, hey, I need you to check your understanding number, whatever. Make sure you include the lesson number at the top. But yeah, we'll do that. Don't forget also, if you have time left in class, you can work on Canvas stuff. So again, due this week is 2.1, 2.2, and 1.5. And then you should be able to go ahead and be working on 3.1, 3.2, and 3.4. Just a heads up, tomorrow's lesson's kind of different. I won't be teaching you anything. You're going to be doing a card sort. So you're going to have a lot of graphs of polynomials, and you're going to have a lot of characteristics about those polynomials. And you're going to try to match them up, which one goes with which. Looking at key characteristics like end behavior. Look at the x-intercepts. Look at the multiplicity of the x-intercepts. Look at the y-intercepts. And I'll try to have the answers posted on here where you can look at them at the end of class tomorrow. But like I said, kind of a weird lesson tomorrow, but I think that's a good one to do when I'm not here because you're supposed to be kind of working on your own anyways. So again, coming up now, I'm going to show the answers, and if there's any of them you need help with or I need to work out more specifically, just let me know, and I can post that on the video tomorrow. So here are the answers. I'm going to zoom in so we can see them. Again, you can just pause the video to check your answers. What they're saying here, the degree of this polynomial would be 3 if you distributed it out, and the leading coefficient is positive, which means no reflection has occurred. So it's in its normal x to the third end behavior. Just like that.